In this lecture, we are just going to do this one exercise. It's kind of a nice first exercise dealing with integrating scalar-valued functions of multiple variables. So imagine that f is a scalar-valued function of n variables, which is continuous on the nice rectangle S. By nice, I mean the sides are parallel to the coordinate axes. What we would like to prove is that if f is continuous on S, then f is integrable on S. I'm going to give you a couple things to think about before we proceed. So take a moment to identify any topological properties that apply to S. So how would you describe S in terms of its qualities? And then what can you say about a continuous function on objects like S? So see if you can kind of see what must be true about F on S. And then a third exercise that I want you to think about before we continue, that is, how should we try to prove that f is integrable? What should be our approach? The questions I asked you are going to go into the proof, but it's also a nice review of some earlier concepts. S is closed because it's a Cartesian product of closed intervals. It's also bounded. So anytime we write this kind of Cartesian product, those intervals are bounded. None of those endpoints goes off to infinity. It's closed, it's bounded, it's a subset of Euclidean space, it's compact. So what we are looking at is a continuous function on a compact set. You can say three things about such a function, a scalar value function. One is that f of s is compact. Maybe I'll write it down. So f of s would be a compact subset of R because f is scalar valued. Again, because f is scalar valued, its outputs are scalars, and continuous functions over compact sets, if you didn't think of it yet, I hope it just came to you, they attain their maximum and minimum values. So the EVT, the Extreme Value Theorem, so we have maxes and mins. Maybe I'll write the sup is a max and the inf is a min. Let me explain what I mean in just a moment. Okay. F is bounded over S. So we know it attains, we know that it has a sup and an inf over S. But the extreme value theorem tells us that there are inputs from S which actually send us to those numbers. So the sup and inf are attained. They are actual output values for the function. So we could actually just call them the max and the min. And then also F is uniformly continuous on S. So a function which is continuous on a compact set is uniformly continuous on that set. Okay. Let me now think about this a little bit. I'll go ahead and tell you that the second one, that the image is compact, this isn't really going to come into the proof. It's a nice thing to remember. I mean, it is a true statement, but we're not going to use the compactness of f of s. However, we will definitely use this statement. This is one that should have jumped right out at you because when we start talking about upper and lower sums, we have this language of sup and inf, but now we'll be able to think of that as max and min. So those are function outputs, and maybe we want to say that those can be close together. But somehow if we make a really good partition, the gap between the tall height and the small height can be made small. And that's going to lead us to a prescriptive way to make a partition of S using uniform continuity. So we will be able to say, the same kind of approach to partitioning S works across F because of the uniformness of F's continuity. Okay, so those are going to come very much into the proof, those two statements there at the bottom. I also want to mention that S is a compact rectangle with sides parallel to the coordinate axes. So are all of the subrectangles that we could create with a partition. So if I want to talk about, after creating a partition, a particular subrectangle, F would also attain a max and min on that subrectangle. So all of the nice things that we can say about F on S, we could also say about F on any subrectangle. I forgot to answer the third question, asking how we will show that F is integrable on S. And what we will do is use Riemann's condition for integrability. This is going to be an exercise now in Scrapwork or brainstorming. So we will probably work kind of backwards and figure out what pieces we need, and then I will show you the complete written proof. Since we're using Riemann's condition for integrability, the first sentence in our proof is going to be let epsilon be greater than 0. We will then want to create a partition of S so that if I compute the upper sum of F with respect to the one and only partition that we create for S and compare it with the lower sum of F with respect to the same partition, ultimately, we want this gap between these two estimates to be smaller than epsilon. So let's start thinking about what this difference will look like. Once we've created the partition, we are going to sum up over the rectangles created by the partition. So I'll add up over all of the subrectangles SI belonging to this partition. You could just write I if you like. But anyway, so we're going to do this finite sum. And for each, we're going to do the sup. Instead of writing out the long description for sup, I'm just going to write sup sub I, meaning the sup over the ith subrectangle minus the inf over the ith subrectangle. Just to save room, let's use that notation, times the volume of the ith subrectangle. Okay, so this is the upper sum minus the lower sum, written concisely with one summation. Now, because F is continuous and each subrectangle is compact by the extreme value theorem, we know that we can take these sup and inf terms and replace them with max and min. So let me just make that switch. I'll probably switch that. And then times the volume again. These are function outputs. Perhaps when we write up the proof, what we'll say is that F attains its maximum over the ith subrectangle at some point d sub I. Wow, that marker's not very good. Let's try this one. Much better. Okay, so these maxes and mins, what's special about these two terms relative to sup and inf is that they are attained. So I can say this max value over the ith subrectangle is equal to some function output at some input di belonging to the subrectangle. Okay, so this is a difference in function outputs over that subrectangle. But now if you think about the definition of uniform continuity, what we say is if 2 points in the domain are suitably close together, then we know that their outputs are within some distance of each other. So what if I could say that I've chosen my partition somehow, I've designed it as we will in a second, so that these two inputs, Ci and Di, are within the necessary distance of each other in the domain. So perhaps we have some idea of delta, and we chop up finely enough so that if Ci and Di come from the same subrectangle, we know that they're within distance delta of each other. Then these two outputs would be, say, within distance epsilon of each other. I'm hesitating there because I might modify that gap, but let's see what it would look like if I replaced this gap in outputs here with epsilon. We're going to go up in size. So this is an estimation. I'm just going to write I right here. So we're saying, okay, what if Ci and Di were close enough so that these two function outputs were within distance epsilon of each other? Then we would have this sum. But the thing is, epsilon is just a fixed number. Pull it out front in front of this sum. Now, adding up the volumes of all of the bases, it's like adding up all of the delta xi's along an interval. It's going to add up to the overall volume of S. Let me go down one more time, like this. All right, and that's not too bad. So I'm saying now that the distance between the upper sum and the lower sum is less than epsilon times the volume of S. S is not something that we are going to change. S is a fixed rectangle, so we were given this rectangle. So whatever the volume of S is, this is just a fixed number throughout this entire exercise. Therefore, I suggest when we pick this, when we pick our delta, we pick delta small enough so that if any two inputs are within distance delta of each other, their outputs are within distance epsilon divided by this kind of global volume, the volume of S. Since that's also a constant, we pull that out here. And that way, at the end, we will have that the gap between the over and under estimates is less than epsilon. Okay, so that is the spirit of the argument. We will have this conclusion. So we've seen how the end of the proof should look. what we now need to do is say, okay, this is the goal. With uniform continuity, our proof is just going to say, like, let delta, or choose delta. So Scrapwork, so let me make it really look like scrap. Choose delta greater than 0 so that if any 2 points, let me just name them x and y, any 2 points from S are within distance delta of each other, so satisfy that their distance in Rn is less than delta, then their outputs are within distance epsilon over the volume of S. We will pause so you can digest this, and then we will talk about now how to make the actual partition. Okay, before I pause, let me summarize what we have worked out on scrap paper so far. What we are going to use is Riemann's condition for integrability, which means comparing the overestimate with the underestimate after we have partitioned S. Then we said, okay, well, we're working with a uniformly continuous function. What we will do is make our partition so that the subrectangles are small enough that any two inputs from the same rectangle are within this distance delta of each other, which means that this difference here, which is greater than or equal to 0, because this is a max and this is a min, so this difference won't be negative. This distance will now be less than epsilon divided by the volume of the entire rectangle S, and then that will work out to show us that our partition is good enough. So we've partitioned the rectangle S finely enough so that the distance between the upper sum of F with respect to that partition and the lower sum are, that distance is less than epsilon. Okay, so I think the Epsilon-delta setup now is ready to go for the proof. I mean, this is Scrapwork, but I'll write it up formally in just a moment. What we need to do now is describe how to partition S so that I know that this will be satisfied for any 2 points from the same subrectangle. We have one more thing to work through before we look at the formal proof, and that is we need to create the partition of S. So I kind of took it as given a moment ago when we started at the very end of the proof, but now we need to go back to the beginning and say how to create the partition S. Okay, so let's see, we're going to let epsilon be greater than 0, then we will pick delta, so that if any 2 points in S are within distance delta of each other, their outputs are within distance epsilon divided by the volume of S. Okay, we want to now partition S so that if I take any 2 inputs from the same subrectangle, I know that they are within distance delta of each other. Now, it's possible that later in life, you might be a little bit less systematic than what I'm about to do. So I'm going to do a very rigorous, thorough way to partition S, and it might not be, you might be a little bit more relaxed and still be correct and rigorous in your proof. However, this is early in our study of Riemann integration, and I want to work through all of the details at least once. Okay, so for S, what I'm going to do is say, let's take each side and chop it in half until the little subintervals that we create through this chopping action are no larger than some bound that will ultimately be something in terms of delta. Okay, so here's what that will look like. Let me take this side first, and I'm going to chop it in half. Okay, these are 2 very wide subintervals, so that's probably not good enough. Let's take these 2 subintervals that we have and chop them in half again. Okay, perhaps it's still too wide, but if you take a number and you keep dividing it by 2, you can get as small as you like. So let's say after my next act of halving, I'm subdividing all of these. Now, when I look at these intervals, they are all less than some recipe in terms of delta. Let me just call this bound capital delta for now, and we will work out what it has to be in just a moment. All right, in this partition, all of these subintervals that I've created along this one sense of direction, they are all evenly spaced. That's fine because I'm just trying to design one good partition. I'm not saying every partition has to have this property. I just want to give you a partition which works for this proof. Okay, let's go along the other sense of direction now. So what's the y direction in this particular picture? Cut in half. Not good enough. Let's cut in half again. And maybe that is good enough. Okay, so you don't have to make the same number of slices in every sense of direction. At this point, I would like to say that this is my partition of the domain. What we want to see now is what has to be true about delta for me to know that any pair of points from the same subrectangle, including these two, which are very far apart, these 2 points I know are within distance delta of each other. You know, for this particular subrectangle, perhaps this is where f attains its minimum on the subrectangle, and this is where it attains its maximum. We will denote it with ci and di just like that. But perhaps in a different subrectangle, they are right next to each other. So there's no fear that they are not within distance delta of each other. They're going to move around, and that's okay. We just want to handle this worst case scenario. All right, so how far apart can these 2 points be? Given that I know all of the sides of the subrectangle enclosing them are less than this fixed measurement capital delta. Okay, so it's just Euclidean distance formula. How far apart are these 2 inputs in Rn? It's the square root of the sum of the squares of the distance and all their coordinates. It's just plain old distance formula. So I'm going to do Ci minus di, Ci1 minus di1. A little bit confusing, but here I mean the ith subrectangle. And here I mean the first coordinate of these vectors. Okay, so this is going to be the second coordinate. If there are little commas in there, might have made it look worse. Second coordinate in these 2 vectors. And we add up all of these squares until we get to the nth coordinate in the 2 vectors. And this is one big square root. Okay. So basically, this is difference in the x-coordinate squared, difference in the y-coordinate squared, all the way through the distance in the nth coordinate squared. This is just regular Euclidean distance formula, giving me the length of this diagonal that I've sketched here. Well, each of these coordinate differences is parallel to the coordinate axes. So if I compare their x difference, that's here. Their y difference is here. So each of these differences is less than delta, capital delta. Maybe that wasn't the best choice in notation, but hopefully writing it down, it's clear. This is less than capital delta squared. So is the second one. All the way through the nth difference. And this is less than. This is a fixed number, capital delta squared. I have n of them. So this expression here is going to be delta times the square root of n. What I want is for these 2 points to be within distance little delta of each other, little delta from the definition of uniform continuity. So if these are within distance little delta of each other, then that means I want capital delta to be less than little delta divided by the square root of n. Okay, don't worry. The phrase capital delta will not appear in the proof. What we are going to do is subdivide in this way so that right from the get-go, each of these subintervals is no larger, or in fact is smaller, than delta divided by the square root of n. So we'll just jump straight to that, leaving the reader to wonder how we knew that was going to be correct, but here it is. This is the justification. And now we are ready to go. At this point, we have talked through the argument behind this proof and looked at each step kind of in a reverse order. So I wanted to just put up the written proof here in 2 stages. Right now, we're going to talk about creating the partition, and then in a moment, we will go forwards with the ending of the proof. I wanted to give you like a nicely written proof, so this is very correct. Starting with let epsilon be greater than 0 as my opening sentence. Then in my usual way, I like to tell the reader how to expect the argument to proceed. So I say specifically that what we're going to do is design a partition named P sub epsilon of the domain S so that Riemann's condition is satisfied. And it might have been even nicer for the reader for me to actually mention Riemann's condition. So as you write this down, do encourage that here. So we're going to show that Riemann's condition is satisfied, namely the distance between the upper and lower sums of f with respect to our partition is less than epsilon. Okay, next we know that we have a continuous function on a compact set, so it's uniformly continuous. Given the epsilon that we have already identified in the first sentence, there exists a positive number delta, so that if I take any 2 inputs from the domain S, which are within distance delta of each other, their outputs are within distance blank. This is the kind of thing where if you're very confident you jump straight to the proof without Scrapwork, you might just leave yourself some space here and go back, fill in later, that you want epsilon divided by the volume of S. And if you're like, well, what if one of the sides is a single point so that the volume of S is 0? I would say that's a degenerate rectangle. It's not really the context, but anytime you're worried about that, what you can do, little trick, is add 1 to it. You'll see later that this works out just fine. So this is a perfectly suitable measurement over here on the right-hand side of this inequality. Okay, next step is to start creating the partition. So I did this very quickly because I was concerned about space, but basically by subdivide, I mean chop in half. So you could write a little bit more about the process there, but take each of the sides, here I'm talking about the kth side, and chop it in half until, vocab word, this word mesh here means maximum subinterval width. So you can use the word mesh to say the max subinterval width. Each one of those needs to be less than delta divided by the square root of n. Jump straight to that bound as promised. And now let the partition that we are going to test Riemann's condition on be this Cartesian product of the intervals that we have subdivided. Take a moment and pause when I step away to look at the notation that I've used here. I try to be very careful with my subscripting. Notice this kind of ending index here is telling you like how many chops were made, and I tried to indicate that it could vary for different intervals. Anyway, it's not a hugely important part of this proof. I just wanted to be very precise for this one example with how I was subdividing those subintervals. All right, what is this giving us? It's giving us a finite collection of subrectangles, and with those subrectangles, we are now going to talk about maxes and mins and do the computation that we need to finish Riemann's condition. We are now ready to compute the upper and lower sums of f with respect to this partition. So first, helping the reader along, by the extreme value theorem, we know that there are points in, say, the ith subrectangle, let's name them Ci and Di, where f attains its minimum and maximum output values respectively. And let's actually tell them where that bound a second ago came from. Notice for each I. So for each subrectangle, the distance between Ci and Di, I'm going to not write out the distance formula. I'm going to just jump ahead a little bit. This is less than the square root of delta divided by the square root of n squared times n. If you think this jump is too far, feel free to fill in the intermediary step there. Okay, n squared, square root of n squared cancels with n. We get the square root of delta squared, which is delta. Consequently, for each I, if I want to compare the sup and inf of our function over, say, the ith subrectangle, I now can really do that. So let me write out the details here. For each I, the sup of the function output values from the ith subrectangle minus the nth is going to be equal to a max minus a min. And I can specifically identify for the ith subrectangle that should be written as f of di minus f of ci. But I just pointed out to the reader that ci and di are within distance delta of each other. So I know that this distance between two function outputs, which is greater than or equal to 0. You don't have to have absolute values here because this one is greater than or equal to that one. But this difference between these two function outputs is less than epsilon divided by, the spirit is epsilon divided by the volume of S. But actually, a second ago, I made a little modification. Okay, and now we are ready to go. I'm going to jump straight to the upper and lower sums, which means I'm not going to rewrite this whole big expression. I'm going to expect the reader to follow me now. Therefore, the upper sum of f with respect to this partition minus the lower sum is going to be equal to the sum over the subrectangles which I'm going to denote as I, this is a finite sum, of actually, I'm going to jump straight to the knowledge we just made, which is that the sup minus nth computation, that's normally what you would write first here, is bounded above by this number. So let me take this equality and replace it with inequality, and we'll write epsilon divided by the volume of S plus 1 times the volume of the base, which is the ith subrectangle. This is a constant number, so I'm just going to pull it out front. And then we are adding up the volumes of all of the subrectangles, but that just adds up to the volume of S. I think what I will do is just scoot this denominator over so that you really see why adding 1 to a denominator that you're worried could be 0 but really should be positive is a safe thing to do, and it keeps you from having to break proofs into cases. It just comes up in analysis sometimes. So maybe you'll see it one day and you'll remember this. But epsilon times the volume of S divided by the volume of S plus 1 could be 0 over 1, which is 0, or it could be, which is less than epsilon, or it could be 4/5, it could be 10/11. It's less than 1, so this is less than epsilon, which is all that we wanted. We didn't have to get equals epsilon over here. Less than epsilon is good enough. So the upper sum minus the lower sum is less than epsilon. Therefore, Riemann's condition is satisfied. And that's all I wanted to do in this video, is just prove this one statement. I think it's an interesting exercise, though. It's nice to revisit those statements we had about continuous functions on compact sets. So this exercise kind of pulls back some earlier knowledge. I also think it's good to systematically create a partition, at least once in your life, but maybe several times. And in this particular exercise, we had a prescriptive way of doing that. And then, bringing in the EVT, I just really enjoy this proof, and I hope you did as well. Thank you for your attention.